Assalamualaikum warahmatullahi wabarakatuh, and very good day to all of you. So, for part number 3, chapter number 4, we will discuss about the example for Soderberg correlation. So, we want to know how to use the correlation that suggests by Soderberg. Okay, as the summary for the Soderberg, as we know, Soderberg introduced the correlation for different cases. So, there are 3 cases in terms of correlation for Soderberg 1949. First case, we have in terms of criteria. The criteria for case number 1 are the aerodynamic load coefficient equal to 0.8, H over B equal to 3, and Reynolds number equal to 10 power of 5, which is equal to 100,000. So 10 power of 5 equal to 100,000. So for the first case, Soderberg suggests the first correlation for nozzle and also for rotor for deflection angle below 120 degree, where we can calculate the loss coefficient for the nozzle by referring to the equation for zeta n star, and for the rotor we can refer to the equation for zeta r star as shown in the slide. For the first case, we have 2 approaches. Whether we can use the equation or we can use the graph of loss coefficient that suggested by Soderberg, where the graph is valid for deflection angle between 0 degree up to 140 degree. So from the graph, if we know the deflection angle, we can determine the loss coefficient zeta star for both, for the nozzle and also for the rotor. And from the first correlation, we will obtain the loss coefficient of zeta star. Okay, second case, the criteria for the second case are aerodynamic load coefficient still 0.8. However, H over V value is not equal to 3, and the Reynolds number still equal to 100,000. So Soderberg suggests the second correlation for this case, where this correlation already involve or already include the correction value, and we can determine the loss coefficient value for the second case by referring to the equation for zeta 1n for the nozzle and zeta 1r for the rotor as shown in the slide. Okay, so from the second correlation we can determine the value of zeta 1. However, in order to determine zeta 1, we need to know the zeta star value, because in the equation will involve zeta n star and also zeta r star. For the third case, the aerodynamic load coefficient still equal to 0.8. However, the value of H over B is not equal to 3, and the Reynolds number also not equal to 100,000. So Soderberg suggests the third correlation, and this correlation also already include the correction. So we can determine the loss coefficient for the third case by referring to the equation for nozzle, which is zeta 2n, and for the rotor zeta 2r. Okay, so for the third correlation, we need to determine the Reynolds number, because in the equation will involve Reynolds number, where Reynolds number equal to rho, density of the fluid, C2, the absolute velocity, dH, the mean diameter at the throat, and mu represent the kinematic viscosity of the fluid. And mean diameter at throat, dH, equal to 2sh cos alpha 2 divided by s cos alpha 2 plus h. In terms of definition of throat, the throat actually refers to the blade opening, or other name for the blade opening is throat. And from the schematic diagram, we can see the definition of throat. Okay, so from the third correlation, we will get the value for zeta 2. However, in order to obtain zeta 2 value, we need to know zeta 1 value and also zeta star value, because in the third correlation, the equation will involve zeta 1n and also zeta 1r value. So from these three correlation, we will obtain called the loss coefficient for different cases, and from this loss coefficient value we can determine the total to total efficiency and also the total to static efficiency. Okay, so this is the summary for the Soderberg correlation that we have learned in part 2. Example 4.2. The figure shows the velocity diagram for a turbine stage with axial flow velocity of 50 meter per second and blade speed of 100 meter per second. By referring to the correlation suggested by Soderberg 1949, determine the total to total efficiency and total to static efficiency of the turbine stage with H over B equal to 5 and Reynolds number equal to 100,000. Assume small temperature difference throughout the stage. So by referring to the velocity diagram and also the data given in the question, such as axial flow velocity, blade speed, nozzle inlet absolute flow angle, rotor inlet relative flow angle, and also rotor outlet absolute flow angle. So you need to determine total to total efficiency and also total to static efficiency. Okay, solution for example 4.2. So related equation that can be used to solve the problem are the equation for total to total efficiency, total to static efficiency, and also the total the equation for work done, where we need to determine the value of H1 minus H3 in the efficiency equation. Okay, so first solve parameter related to velocity diagram with data given, where Cx equal to Cx1 equal to Cx2 equal to Cx3 equal to 50 meter per second. So we will have constant axial flow value as we learned in previous chapter. Okay, and because if you look at the equation will involve numbers of parameter that can be obtained by using the velocity diagram. Okay, so we have u equal to 100 meter per second, alpha 1 40 degree, beta 2 60 degree, and alpha t equal to 45 degree. Okay, at the nozzle inlet, so the figure shows the velocity diagram at the nozzle inlet. So we have C1, Cx1 equal to 50 meter per second, alpha 1 equal to 40 degree. Okay, so now we want to determine the absolute flow velocity C1. So by referring to the trigonometry formula, so cos alpha 1 equal to Cx1 divided by C1, where C1 equal to Cx1 divided by cos alpha 1. So from the equation we can determine C1 value, where C1 value will be equal to 65.27 meter per second. At rotor inlet, the figure shows this velocity diagram at the rotor inlet. So we have the information in terms of Cx2, beta 2, u value, blade speed, and we need to determine the value of alpha 2, C2, W2, WY2, and also CY2, because later on we will need to use this value to determine the efficiency, total efficiency also, and also total static efficiency. So first we want to determine the y component for absolute velocity CY2 by referring to the trigonometry formula. Cos beta 2 will be equal to Cx2 divided by W2, and we will get from the equation we will get the value for W2, relative velocity at the inlet of the rotor, and the value will be equal to 100 meter per second. And tangent beta 2 equal to the Wy2 divided by Cx2. So we can determine the Wy2 value, where Wy2 equal to 86.60 meter per second. Okay, and from the value of Wy2 we can determine Cy2 component, where Cy2, if you refer to the velocity diagram, Cy2 equal to Wy2 plus u, where we will obtain the value of Cy2 equal to 186.6 meter per second. In terms of absolute flow angle alpha 2 at the rotor's inlet, we can determine by using tangent value, where tangent alpha 2 equal to cy2 divided by cx2, and tangent alpha 2 will be equal to 3.732, and alpha 2 value will get the value which is equal to 75 degree. By using trigonometry or triangle law to determine absolute velocity C2, first we need to know the value of theta. So theta actually equal to 180 degree minus 90 degree minus 60 degree. So we'll get theta value equal to 30 degree. So from the triangle, we can manipulate the value of theta and use the equation involved with triangle, where C2 square equal to W2 square plus U square minus 2W2 U cos 180 degree minus theta. So from this equation we can determine C2 value, which is equal to 145.46 meter per second. Okay, at rotor's outlet, the figure shows the velocity diagram at rotor outlet. So we have, in terms of data given, so we have U value 100 meter per second, alpha 3 45 degree, cx3 equal to 50 meter per second, and we need to determine beta 3, w3, c3, cy3, and also wy3. So for absolute velocity c3, use the tangent formula, tangent alpha 3 equal to cy3 divided by cx3, where cy3 equal to cx3 tangent alpha 3. So we get the value for cy3 equal to 50 meter per second. And we know that from the velocity diagram, wy3 actually equal to cy3 plus u. So cy3 equal to 150 meter per second. Then we can determine the value of C3 from the cos formula. So cos alpha 3 equal to cx3 divided by C3. So C3 will be equal to 70.71 meter per second. Okay. By using the trigonometry or triangle law, we can determine W3, where if you refer to the Pythagoras theorem and look at the triangle, so W3 square equal to WY3 square plus CX3 square will be equal to 25,000. Square root the value, so we'll get the value for W3, which is equal to 158.11 meter per second. And then we determine the relative flow angle beta 3, tangent beta 3 equal to wy3 divided by cx3, it will be equal to 3.0. So the value of beta 3 equal to 71.56 degree. Okay, for the enthalpy difference, we know that from the basic stagnation enthalpy equation, H naught equal to static enthalpy plus half C square. So rearrange the equation, so we will get the basic equation for static enthalpy. H static enthalpy equal to stagnation enthalpy minus half C square. Okay, by referring to the equation, we will get the equation for static enthalpy difference H1 minus H3. Substitute the equation, so we will get H1 minus H3 equal to H01 minus H03 plus half C1 square minus C3 square. And H01 minus H03 actually equal to U multiplied by CY2 plus CY3. So previously we already determined the value of CY2, CY3, C1 and also C3. So we can determine the value of H1 minus H3. Okay, substitute all the data obtained related to the enthalpy difference equation. So we will get the static enthalpy difference equation or value equal to 23,290.13 joule. Okay. Okay, in terms of loss coefficient value, because in the total efficiency and also total static efficiency equation, the equation will involve the zeta value, which is referred to the loss coefficient value. So loss coefficient value, in order to determine loss coefficient value, we need to determine by using the Sonderburg correlation. So based on the question, the case is for h over b not equal to 3 and Reynolds number 100,000. Thus, we need to determine zeta star and also zeta 1. And zeta 1 value will be used in the efficiency calculation for total to total and also total to static efficiency. So differentiate first, we need to know the differential angle for nozzle and also for the rotor. So we know that differential angle for the rotor equal to alpha 2 plus alpha 1. We already calculate alpha 2 and alpha 1, just substitute the value. So we'll get deflection angle for nozzle equal to 115 degree. For the rotor, deflection angle for the rotor equal to beta 2 plus beta 3, and also we already also determine the value of for beta 2 and also beta 3, and the value will be on 131.56 degree. So use the I call the value of deflection angle to determine the loss coefficient by using the Sonderburg loss coefficient correlation. So for the first Sonderburg loss coefficient equation, so we can obtain zeta n star by using the equation shown in the slide, and we get the value for zeta n star is equal to 0.1193. Okay, for zeta r star formula, we need to substitute the differential angle for rotor epsilon r value, and we'll get the value for zeta r star equal to 0.1438. Okay, because the case involved in the problem, the value of h over b is not equal to 3, so we need to consider the second correlation of the Sonderburg equation, where the second Sonderburg loss coefficient equation, where h over b equal to 5. So in the nozzle, we need to use the formula for zeta 1n, substitute the value for zeta n star and also b over h value into the equation. So we'll get the value for loss coefficient for the nozzle after we consider correction, where the value for zeta n that we need to substitute into the efficiency equation is equal to 0.1162. And in the rotor, the zeta 1r value is equal to 0.1324, which is also equal to zeta r value that we need to substitute into the total and also total to static efficiency equation. Okay, so we already got all the value that required to calculate the turbine stage efficiencies. Okay, so substitute all data related to the total to total efficiency equation. So we have this equation because we already neglect the temperature difference, so we need to use this equation. So we already calculate the value of zeta r, w3, zeta n, c2, and also h1 minus h3. So substitute all the value. So the value for total efficiency is equal to 88.98%. However, for the total to static efficiency, use the similar method, because now we already have all the value that needed to substitute into the equation. So we have zeta r, w3, zeta n, c2, c1, h1 minus h3. Just substitute all the data, so we can obtain the value for total to static efficiency, which is equal to 82.28%. Okay, that's how we use the Sonderburg correlation in in the problem that involves a turbine stage. Okay, in order to test your understanding for part number 3, chapter number 4, please answer the question. First question: state the conditions where we need to consider all correlation that's suggested by Soderbergh 1949. Question number 2. What is the basic knowledge need to be used to determine unknown vector component in a velocity diagram? Question number 3. What is the difference between total to total efficiency and also total to static efficiency? So you have to answer the question by clicking the link provided in my blog. Remember that you need to know the password in order to open the link. The password was given throughout the video related to this topic. The clue is also given in the link. So that's all for part number 3, chapter number 4. Assalamualaikum.